Hi dear students, our next topic is cycloid motion. Here we discuss the motion of the electric charge in the transverse electric and magnetic field. The motion of the electric charge in the transverse electric and magnetic field means the electric and magnetic field are perpendicular to each other. In that field, an electric charge moves, and what will be the trajectory of that electric charge? That we will discuss here. As the name it suggests, cycloid. Everybody know the motion of the cycle tire. If we consider this cycle and the point on this wheel, that is here, the tire, when the cycle starts to move, then this point, if you concentrate on this point, and if this is a road, then that point is now here, cycle tire rotates, and the point also move, and if this is time is equal to 0, the next time, and when it rotates in this clockwise direction, or if the cycle moves in this positive x direction, then the motion, if you concentrate on this point, then you can see that this will be like this. Point to rotate, and right just this point, and again rotate to this point, and this will be the trajectory of that point that we marked on the cycle tire. That is, if we keep our electric charge in a transverse electric and magnetic field, then that charge also follows the same path. That is why the name is called cycloid motion. Okay. Let us examine how this happens, how the charged particle occurs this trajectory motion. Okay. That is our next discussion. That is, if the magnetic field is applied along the x direction and the electric field is applied along the z direction, then the trajectory of the charged particle will be along will be this one, and we will answer this question. That is, when a charge at the rest is released from the origin, that is at this point, then what path will it follow? The answer is that it will follow this path, but how this path is achieved by this particle, that is we will discuss here. The question is this one. Okay, in a transverse electric and magnetic field, a charge at rest is released from the origin, then what path will it follow? The charge is released at the origin. At the origin means our charge is here. In this picture, our charge is kept here. Let Q be the charge. Then here the magnetic field B, that is applied along this positive x direction. Therefore, we write this magnetic field B is equal to BI. That is, the magnetic field is coming out of the page. If I denote this direction of the magnetic field, this one, the field is coming out of the page. The electric field is applied along the z direction. That is, that electric field can be represented by E is equal to EK. The direction of the electric field is along z direction. Fine. When the charge is kept at the origin, then the electric field, this field, exerts some electric force on the charge Q. That is, at the origin, the electric field E exerts a force on Q. That force F is equal to Q into E, because if a charged particle is kept in an electric field, that charged particle Q experiences a force, that is Q into E. The direction of that force is along the direction of the applied electric field if it is a positive charge. That is, this charge experiences a force in this direction. Similarly, here, the charge here experiences a force on this direction. That is, if I draw the axis here, our electric field is here, our magnetic field is around this direction, and our charged particle starts to experience a force in this direction. That force is an electric force, right Fe, and along that direction, the charged particle starts to move. Or we can say, along this direction, the electric field accelerates the charge. The electric field accelerates the charge along this Z direction. This is Z direction, this is a X direction, and this is a Y direction. Therefore, the charged particle get an acceleration along this direction. The electric field accelerates the charge along Z direction. Then let us say that force F, that is nothing but ma. That force F is equal to QE. The charge occurs an acceleration. The magnitude of the acceleration is given by QE divided by M. Because this is we have written from this one. Force F is equal to ma, and the right hand side is QE. Then, as soon as the charge occurs this velocity, and on this direction, there is the charge now occurs a acceleration and thus a velocity. Acceleration is nothing but the change in velocity with respect to time. Then, when the charge gets an acceleration, it means the charge occurs a velocity v. If a charge is moving in a magnetic field B, then with a velocity v, then the force experienced by the charged particle, that is given by the orange force, F is equal to Q into V cross B. Okay. That is, as soon as the charge occurs a velocity, a magnetic force develops. That is, the charged particle starts to experience a magnetic force F. That is, the charged particle starts to experience a magnetic force. Find that force is given by F is equal to Q into V cross B. That is, here, if you plot, if you mark direction of the magnetic field that is coming out of the board, that is, we have noted like this, that is along the positive x axis. The velocity of the charged particle is, that is, around this direction v, and to find out the direction of the magnetic force, we have to apply the right hand palm rule. That is, this right hand palm rule I explained in the previous lecture. You can use either this right hand palm rule or the Fleming left hand rule to find out the direction of the magnetic force experienced by the charged particle in the magnetic field B. If you apply the right hand palm rule, then the magnetic field is coming out of the page. Therefore, you keep your palm the outside direction, then stretch your thumb this fashion. Here, the fingers, that is around the direction of the velocity of the charged particle, and the palm is directed out of the page, and this thumb gives the direction of the force. That is, our charged particle experience a force around this direction, F. Or if I draw the picture here, the charged particle, because of the electric field, starts to move along this direction. As soon as the charged particle acquires a velocity v, it starts to experience a magnetic force along this direction. Therefore, the trajectory of the particle will change into the direction of the force. Now, if the charged particle moves around this direction, its velocity is in this direction, that is, the velocity is around this direction. Here the magnetic field is still pointing out of the page. Then if you apply again this right hand palm rule, then you will see that the direction of the force experienced by the particle will be along this inward direction. That is, the force experienced by this particle is inward this direction. Again, the trajectory of the particle will be changed in this direction. And if the path is along this one, the velocity will be along this direction. When the charge is moving along this direction, that is the down to the y-axis. This is our y-axis. This is our x-axis. This is our z-axis. And when the charge moves down to this y-axis, this is against the motion of the electric field. That is, the electric force is along this direction, but because of the effect of the magnetic force of the charged particle is coming down and touches on the y-axis. That is, here the electric force is opposite to the velocity of the charged particle, or is opposite to the direction of the electric field. Then the velocity of the charged particle decreases. അതായത് നമ്മുടെ ഈ പിക്ചറിലെ നമ്മുടെ ചാർജ്ഡ് പാർട്ടിക്കിളുടെ ഒരു വി വെലോസിറ്റി ഈ അപ്ലൈ ചെയ്തിരിക്കുന്ന ഇലക്ട്രിക് ഫീൽഡ് മൂലം ഇലക്ട്രിക് ഫീൽഡ് ഫോഴ്സ് കിട്ടും. അതിന് ഫലമായിട്ട് സെഡ് ഡയറക്ഷനിൽ നമ്മുടെ ചാർജ്ഡ് പാർട്ടിക്കിളിനെ മുകളിലോട്ടേക്ക് മൂവ് ചെയ്യാൻ തുടങ്ങും. ഒരു പർട്ടിക്കുലർ വെലോസിറ്റി അതിനെ അച്ചീവ് ചെയ്യാൻ തുടങ്ങുന്ന സമയത്ത് തന്നെ അതിനൊരു മാഗ്നറ്റിക് ഫോഴ്സ് കിട്ടി തുടങ്ങും ചാർജ്ഡ് പാർട്ടിക്കിൾ. കാരണം ഇവിടെ ഒരു മാഗ്നറ്റിക് ഫോഴ്സ് ഒരു മാഗ്നറ്റിക് ഫീൽഡ് നമ്മൾ ആദ്യമേ അപ്ലൈ ചെയ്തിട്ടുണ്ട്. This outward direction. അപ്പോൾ വി വെലോസിറ്റിയുള്ള ചാർജ്ഡ് പാർട്ടിക്കിൾ ബി മാഗ്നറ്റിക് ഫീൽഡ് മൂവ് ചെയ്യുകയാണെങ്കിൽ അതിന് അനുഭവപ്പെടുന്ന ഫോഴ്സാണ് ഈ ലോറൻസ് ഫോഴ്സ്. ആ ഫോഴ്സിൻ്റെ ഡയറക്ഷൻ നോക്കിക്കഴിഞ്ഞാൽ മനസ്സിലാവും. ഈ ഒരു പോയിന്റിലെത്തുമ്പോൾ അതിൻ്റെ ഫോഴ്സിൻ്റെ ഡയറക്ഷൻ റൈറ്റ് സൈഡിലേക്ക്, അതിൻ്റെ ഫലമായിട്ട് ചാർജ്ഡ് പാർട്ടിക്കിളിൻ്റെ പാത്ത് പതുക്കെ ചേഞ്ച് ചെയ്തിട്ട് ഈ ഫോഴ്സിൻ്റെ ഡയറക്ഷനിലേക്ക് ആകുമ്പോൾ ചെറിയൊരു ഡീവിയേഷൻ ഉണ്ടാവും. ഡീവിയേഷൻ കിട്ടിക്കഴിഞ്ഞാൽ അതിൻ്റെ മോഷൻ ഇങ്ങനെയായി. ഈ ഡയറക്ഷനിലാണ് വെലോസിറ്റി എങ്കിൽ ഇവിടെ നമുക്ക് ഈ ചാർജിന് അനുഭവപ്പെടുന്ന മാഗ്നറ്റിക് ഫോഴ്സ് കണ്ടുപിടിക്കാൻ നമ്മൾ അപ്ലൈ ചെയ്യുന്നത് വീണ്ടും റൈറ്റ് ഹാൻഡ് പാം റൂൾ. അത് ഉപയോഗിച്ച് കഴിഞ്ഞാൽ നമുക്ക് മനസ്സിലാവും അതിനനുഭവപ്പെടുന്ന ഫോഴ്സ് ഡൗൺവേർഡ് ആണെന്ന് മനസ്സിലാവും. ഈ ഫോഴ്സ് എന്ന് പറഞ്ഞാൽ മാഗ്നറ്റിക് ഫോഴ്സ്. വീണ്ടും നേരെ ഇങ്ങനെ പോകുന്നതിന് പകരം താഴെ ഒരു ഫോഴ്സ് കിട്ടുന്നത് കൊണ്ട് വീണ്ടും പാർട്ടിക്കിൾ വിൽ ബി ചേഞ്ച്. ഓക്കെ, അപ്പോൾ ഇങ്ങനെ താഴോട്ട് വരുന്ന സമയത്ത്, അതായത് നമ്മുടെ ഇലക്ട്രിക് ഫോഴ്സ് ഈ ഡയറക്ഷനിലാണ് ഉള്ളത്, പക്ഷേ മാഗ്നറ്റിക് ഫോഴ്സിൻ്റെ എഫക്റ്റ് മൂലം ചാർജ്ഡ് പാർട്ടിക്കിളിൻ്റെ സ്പീഡ് വെലോസിറ്റി ഈ ഡയറക്ഷനിലേക്ക് മാറി. അപ്പോൾ നമ്മുടെ വെലോസിറ്റി ഇങ്ങോട്ട് ചാർജ് പാർട്ടിക്കിൾ ഈസ് കമ്മിങ് ഡൗൺ, അതായത് മാഗ്നറ്റിക് ഫോഴ്സ് ഈസ് അപ്വേർഡ്. ഇത് രണ്ടും ഓപ്പോസിറ്റ് ആയതുകൊണ്ട് that is the velocity of the charged particle is against the E, and hence the charged particle deaccelerates. When the charged particle is coming down and touches on this y-axis, then the charged particle starts to deaccelerate. Deaccelerate means the velocity decreases when the velocity, if the velocity decreases, then the magnetic force F is equal to Q into V cross V also decreases, because if V is only the changing parameter here, charge and magnetic field strength are constant. When V decreases, then this force will also decrease. The magnetic force decreases. Okay. Then, when the charged particle touches on this y-axis, that is, if you come back to this picture, the charged particle touches this y-axis, after following this curved path, the force Fb becomes 0. That is, magnetic force becomes 0 because the velocity approaches to 0. Here, still the electric field is there. This applied electric field again accelerate or apply some force on the charged particle. As a result, our charged particles moves around the direction of the electric field. F is equal to U into E. Once again, the charged particle is accelerated in the positive z direction. As soon as the charged particle achieves the velocity v, again it experiences a magnetic force. The direction of the magnetic force will be in this direction. Around that direction, the charged particle starts to deviate or starts to travel. Here, still the particle has certain velocity v. As a result, the magnetic force will be acting around the downward direction. The path will change to this one. When the charged particle reaches this position, like here the velocity v is against the applied electric field. Therefore, the charged particle starts to deaccelerate. The velocity decreases. Therefore, the magnetic force decreases. And when the charged particle reaches the y-axis, the magnetic force Fb will be 0. And when the charged particle touches on the y-axis, again the electric force starts to act on the charged particle, that accelerates the charged particle around this positive direction, and the cycle repeats. In this way, the charged particle follow this path. That is, particle moves along this one, touches the y-axis, again increases, reaches the velocity 0. Again, it is accelerated by the electric field. Then the magnetic force brings the charged particle to the curved path. In this way, our charged particle follows a path, and the path followed by the charged particle, the transverse magnetic and electric field is called cycloid. Cycloidal motion means the motion of the charged particle in the transverse electric and magnetic field. I hope this is clear to you. And now I would like to bring your attention on another point. That is, here this magnetic force does not do any work. We have seen that the magnetic force does not accelerate the charged particle. Therefore, this magnetic force does not do any work. Let us prove that magnetic force does not do any work. That is, we know to find out the work is given by force and displacement. That is, here the work is done by the magnetic force. Therefore, we can write F magnet dot displacement is dr. In a magnetic field exists in a certain region, our charged particle Q starts to move or starts to enter, then it travels a distance dr. That is, if Q moves a distance dr, then the velocity of that charged particle, that is dr by dt, or we can write the distance moved by the charged particle in a short time dt is dr is equal to v dt. Here I write this force as a F magnet, that is nothing but Q into V cross B. Instead of this dr, I can write this v dt. Then our aim is to show that the magnetic force does not do any work. That is a work done by the magnetic force that is equal to 0. We have to prove this one. Here if we check, this Q into V cross B is nothing but the magnetic force. The angle between this magnetic force and the velocity of the particle, that is, if the charged particle is moving on this direction with the velocity v, using the right hand palm rule or using the Fleming left hand rule, you will see that the force will be along this direction. It's a magnetic force. We have already discussed this direction of the force in the previous lecture. The angle between this force F and the velocity v, that is, in this picture, this is the angle theta. That is, we can say that if this force and this velocity are perpendicular to each other, the angle between them theta is equal to 90 degrees. Fine. Therefore, V cross D, that is the force, is perpendicular to the velocity v. Therefore, we can write the dW, work done by the magnetic force, that is equal to Q into V cross B. V, that is cos theta. Here cos theta is 90 degree. This is equal to 0 because cos 90 is equal to 0. That is, the magnetic force does not do any work. The meaning is this one: the magnetic force does not increase the speed or decrease the speed of the charged particle. That is, the magnetic force does not do any work. Fine. The charged particle can be accelerated by the electric fields only. The magnetic force does not increase or decrease the speed of the charged particle. Thank you very much.